Good morning, good afternoon, good evening, whenever you're watching this. Ladies and gentlemen, we're going to do our the last notes from chapter 3, and that is section 3.9, differentials. And your assignment is 1 through 20 even, so that's only 10 problems. And I will tell you, it almost seems like you're doing nothing in this section, but there is. And this is a very conceptual use of the derivative. And again, it's the final notes that you'll be taking in chapter 3. So let's see real quick. Okay. Recall section 3.8, which we just finished and went over, was on Newton's method. It used a tangent line to approximate the roots of the graph of f. Okay, so if I wanted to find out where f crossed the x-axis, I could use a derivative in Newton's method and certain iterations of Newton's method to find the actual root without actually solving an equation, just using a tangent line. And this is what makes it really, really neat. In this section, we'll use a straight line, the tangent line, to approximate the function, the curve. So how can a straight line approximate a curve? So consider the function that is differentiable at c. The equation for the tangent line is the following. And you know this. You already know this. You've seen this over and over again. That y is going to equal f at c plus f prime at c times x minus c. This is just the point slope form solved for y. Okay? Now, realize that if we look at the values close to c, we can use the corresponding y values as an approximation of the function. Again, if you have a tangent line at some value, and we'll call it c, small windows around that c value will approximate the function itself. Okay? This is still kind of Newton's method, but it's Newton's method not to find the zeros, but to find any value on the function. Here's what we're basically talking about. You have some curved function and a straight line, and they're tangent at one point, this red point C, right? Well, if we zoom in and we get really, really close to that C value, okay, we can almost see, even though it's pixelated, we can almost see that the straight line and the curved line are basically the same values around C. Now, granted, this window would have to be really, really, really tiny. And that's where we use the limit process. We go, okay, well, let's take the limit and let's get really, really close to C on both sides. That will help us approximate what the function is. And we're not looking at the roots this time. We're actually looking at values. This is called linear approximation. We're approximating a curve by a straight linear line. Okay. And again, it's a conceptual idea, but you have to think, okay, well, hey, we were able to find the roots. Well, why not find just any value on the function? Realize that if we look at values close to c, we can use the corresponding y values as an approximation of the function of f. And that's exactly what we're just looking at right here. Notice that looking at very small values around c, the graph of f actually becomes a straight line. Also notice that this tangent line will only approximate the values of c at that c value. To find another point of f, another tangent line would have to be found. So again, the approximation is only good for that one c value. If you want to find another c value, like, oh, I want to know what it is down the function, if you wanted to find that, you'd have to find another c value, and again, repeat this entire process again. When the tangent line at c comma f and c is given by, and then again, it's just going to give you that same one. I mean, we just have to redo the the function itself, the what is this? The tangent line equation. I couldn't think of it. Again, it's the y and the y value plus the slope times the x minus the x value. In this case, it's c. This is used to approximate f. The quantity x minus c is denoted as delta x. So x minus c is actually the change of x. And when x is really, really small, okay, again, from the left and the right, we saw that picture, when you get really, really close to that red dot, then the change in y is denoted as the change of y. It's called delta y. And that can be approximated by f of c plus delta x minus f of c. You know, basically we're breaking down the slope. Remember, the change of the y, or delta y, is always how when you subtract the two y values. Since we're letting delta x get really, really tiny, okay, we're using our limit process, this f of c plus delta x minus f of c is going to be the change of the y. And again, a very small change of y. This is really the derivative times the derivative at c times the actual change of x. Okay. Now, this is really funny because as I was looking at this, you know, I've been teaching calculus for a while, and I look at this, I'm like, hey, this is just the definition of derivative. Because if I were to just divide both sides by delta x, I would have f at c plus delta x minus f at c over delta x. And that's the definition of the derivative. Well, what they've done here is they've actually multiplied both sides by delta x, and we got the function, the derivative of the function at c times delta x. Okay, and this is what we're breaking down. We're breaking down what they call the differentials. Delta x and the delta y are the differentials. And that's it. That's it. That's the notes. I mean, it's a very conceptual thing. We're actually going to do examples in class, but what I want you to get out of this video is that we're looking at small, tiny windows around a particular x value, and that means that our y values, the change of the y, is also going to be very, very small. And basically, essentially, what you're going to be doing, you're going to take the derivative of a function, you're going to plug in that particular c value, and you're going to subtract the two x values to give you your delta x. That's going to give you your delta y, the change of the y. And right now you're like, that doesn't make sense to me. Well, when you see it, when you do the actual problems, you'll see it a little bit more. Thank you for watching the video. Like and subscribe. And come to class so we can do some problems.